Okay. Hi, everyone. My name is Linsen, a second-year PhD student in Rensselaer Polytechnic Institute in Professor Tong Zhang's group. And today it's my honor to present our paper, ZipKV, in memory key value store with built-in data compression, and share our findings and thoughts with you. Let's begin by discussing the current landscape of in-memory data store. As many of you know, memory, particularly DRAM, serve as a core and important component in data store. However, with the slowing of Moore's law and the global supply shortage in recent years, the cost of DRAM has become a significant burden for major cloud service providers. For example, memory costs reportedly account for up to 50% of Microsoft Azure server cost. Despite these financial implications, there has been a lack of focus on reducing memory usage. The industry and academia's attention is predominantly directed toward performance, often at the expense of memory efficiency, because there is a prevalent belief that implementing compression, a straightforward method for memory saving, leads to substantial performance degradation. This belief has deterred many from considering compression as a straightforward method to saving memory. Driven by these realities, our team has focused on the increasingly important task of reducing memory cost. Furthermore, our team believes that it is crucial to understand that in-memory key value store are just one component of a larger system. As such, they don't necessarily need to be the fastest part of their system. Instead, they simply need to perform well enough to avoid becoming a bottleneck. This perspective has guided our approach and allowed us to prioritize memory efficiency without sacrificing the overall performance of the system. So, before we dive into the specifics of our ZipKV design, let's take a moment to understand the foundation of our work, general-purpose lossless block data compression. This isn't a new or flashy concept. In fact, it has been explored and evolved over several decades. At its core, general-purpose lossless block data compression is typically built upon LZ search. Despite the various iterations and advancement over the years, LZ-based compression method often faces a trade-off between search quality and speed. Moreover, as we can see in this diagram, it is common to observe a significant difference in speed between compression and decompression. As you can see, decompression is typically much faster than compression in any level of the LZ search. So, in our exploration of LZ-based compression method, we discovered a simple yet powerful feature. LZ compression method supports early termination during decompression. This means users have the flexibility to end the decompression process whenever they choose, instead of decompressing the entire block to its original compressed size. As illustrated in the diagram, you will notice that the decompression latency is directly proportional to the termination location. This feature has significant implications for our work and the design of ZipKV. Drawing on these motivations and findings, we have developed our design solution. Generally, key value pairs reside in moderate-sized pages, such as 4 kilobytes, each of which is compressed using LZ-based libraries. For indexing, we handle key-to-page mapping using hash or B+tree structures. However, this approach raises a significant question. How can we effectively manage the data access latency overhead induced by compression? This question has been a key focus in our design process. To address the challenge of compression-induced data access latency overhead, we divide the problem into two parts, reducing read amplification and write amplification. Let's first discuss our approach to reducing read amplification. We have introduced the concept of intra-page direct key-to-subpage hashing. In this method, we partition each page into equal-sized subpages and use a hash function to directly map key-value pairs to their target subpage. On average, each subpage is approximately half filled, with the remaining space filled with dummy content, such as or 0 or 1. That is compressed using LZ-based compression method. A random key-value pair is expected to be located in the middle of the page, and this distribution allows us to leverage the early termination during decompression, significantly reducing read latency. Moreover, we further reduce read amplification through intra-page hot KV pairs promotions. Taking into account the temporal locality of data access in real-world workloads, we have added a hot data subpage P0 at the front of each page. During the page recompression process, key-value pairs that are frequently read are promoted to P0 at the front of each page. This strategy further leverages the benefits of early termination during decompression, resulting in even more efficient read operations. And our final flowchart for search a key from the page should be like this. First, check the Bloom filter first. If Bloom filter gives us a positive, which means that there is a very high possibility that the KV pair is reside in P0. So first we reconstruct P0 with very short latency. However, if the Bloom filter result gives us a false positive, which means the P0 does not include the desired key-value pairs, we will reconstruct the remaining subpages to search for the key with relative longer latencies. At both reconstruct operation utilize decompression early termination we mentioned before. Moving on to the reduction of write amplification, we have introduced a two-tier write buffer design. Firstly, we employ a very simple per-page landing buffer to merge multiple write requests. This approach helps to mitigate the compression overhead associated with each write operation. Secondly, considering the time overhead difference between compression, which is slow, and decompression, which is fast, we have added a second tier of buffering. This delta buffer uses delta encoding to store the difference between the most recent key-value content and the older key-value content and store the difference in the delta buffer. This strategy can further improve buffering effectiveness and delays compression overhead, trading off against the decompression, relative quick decompression. In this way, we can further optimize the write operations. Lastly, to support our proposed solution and enable scan support, we have developed a hybrid indexing data structure that combines the advantage of both pure hash-based and pure B+-based index, B+tree index. This hybrid tree hash index data structure is a key component of our design and plays a crucial role in the overall performance of the functionality. You can see in the diagram that in the top upper part of the indexing, we utilizing a B+tree index. However, when we go down to the separate page, in terms of separate page, we use direct hash to do the page index. So, and moreover, we give user the freedom to choose to tune our indexing method between pure B+tree to pure hash-based index. So, which means if you do not consider scan support, you can only use pure hash-based index. And if you want a very quick a scan support, you can choose pure B+tree design. By combining all of the proposed design solutions, we have developed our prototype, ZipKV. ZipKV incorporates these design techniques to address the challenges of compression-induced data access latency overhead. ZipKV provides support for essential key-value store operations, include get, put, delete, and scan queries. Additionally, we have designed ZipKV to be flexible, allow users to configure important parameters according to their specific requirements. To evaluate the effectiveness of our proposed design, we conduct a comprehensive benchmark study. We compare ZipKV against well-known in-memory data stores such as RocksDB, Redis, Faster, and Mastery using the Yahoo Cloud Serving Benchmark, YCSB, benchmark tool. In our benchmarking, we optimize RocksDB for pure in-memory mode according to a guide by the developer, and enable compression for RocksDB and ZipKV, and leave others in non-compression mode because Redis and Faster and Mastery, they do not support compression in their design. Moreover, we tested ZipKV in both direct hash and full tree mode. The tests were conducted on a high-performance server with 32-thread Intel Zhang CPU and 384 GB DRAM. The raw data size used for the baseline test was 28 GB. Analyzing the result of our baseline compression, it is evident that the non-compression speed optimized Faster achieved the highest throughput across all the baseline tests. However, when comparing compression-enabled data store, ZipKV consistently outperformed RocksDB. The performance gap between ZipKV and RocksDB become more pronounced in write-intensive workloads like YCSB-A and update only, primarily due to the higher write amplification experienced by RocksDB for their log structure merge tree design. Despite this, both compression-enhanced ZipKV and RocksDB achieve similar memory consumption levels, outperforming other faster but more memory-intensive competitors. To provide more conclusive insight, we conducted a workload sensitivity study to examine the impact of data access locality and data compressibility on the performance of the data store. From the result depicted in the diagram, we observed that compared to RocksDB, ZipKV exhibits greater benefits in read-intensive workloads as the data locality increases. This can be attributed to the effectiveness of the intra-page hard KV promotion for high localized data. Regarding data compressibility, our finding indicates that update-intensive workloads are unaffected by the data compressibility. However, for read-intensive workloads, the performance is dependent on the level of data compressibility. From the table shown, we can tell that the latency of CPU-based decompression tend to reduce as the data are more compressible. In addition to our workload sensitivity study, we also conducted a configure sensitivity study for ZipKV, focusing on the indexing structure configuration and write buffering configuration. Regarding index structure configuration, we found that by tuning the hybrid index B tree more towards B+tree direction, we observed an increasing in throughput for YCSB-E, which is scan operation, while experiencing a decrease in throughput for update-intensive YCSB-C operation. These trade-offs arise from the balancing act between index complexity and scan support. In our write buffer configuration test, we observe another trade-off between write performance and memory consumption. As we increase both the delta buffer and the landing buffer size, the throughput will increase at the expense of memory consumption. To conclude, the team explored the possibility and facilitated the integration of block data compression into in-memory key value data store, and proposed ideas to reduce compression-induced performance degradation and demonstrate our idea through experiments and benchmark. And thank you for your time and attention. And now I am open for questions. Thank you.
All right, any questions? Very interesting system. What you call read amplification, there's a P0.
Yeah.
Is it a cache? In the sense that you mentioned promotion, do you also evict?
Yeah. I think for smaller data set, the P0 will be in cache, but for a larger data set size, the cache cannot hold the entire.
No, I meant yes, I agree that cache hardware cache, CPU cache may not be large enough.
Yeah.
But I'm asking, in your system, how do you manage P0? You're moving blocks into P0, that's promotion. But what happens if it's full? P0 is full. If you have something also frequently accessed, what do you do?
Oh, if P0 is full, because actually in our design because we utilize compression to already saving the memory. Mm-hmm. As a result, when do promotion, we keep the for example, we keep the key value pair at its original location, for example, P5, and have another copy of it into P0 as a cache. So if it is not hot enough to stay in P0, we just it will be evicted and go back to its original place. Yeah. Thanks.
So I might have missed this. What if you use a compression algorithm that allows you to decompress subblocks or indexes into subblocks?
You mean the partial decompression?
Yeah.
I think partial decompression is currently we mainly use LZ4 for partial decompression, and because LZ4 is a very relatively simple compression method, only utilize the LZ compression. So it originally supports partial decompression. So we're just using the API they give us. But for compression methods like ZSTD, because it is a combination of LZ compression and entropy encoding, which means it cannot directly support the partial decompression. In that case, we divide our page, our 4K page, into several different subpages, like 1K, 1K, and 1K. And then we compress 1K page as a block in ZSTD. And when we want to do some decompression, we just decompress the 1K block to decompress the 1K block. Instead of decompress the entire 1K block for longer latency.
So in that mode, do they share a dictionary, those different compressed subblocks?
That's a good question, but I think maybe they do not share the same dictionary. Yeah. So the compression efficiency will be a trade-off. Yeah.
Hello. Thank you for an interesting talk. As far as I see it, right, in your key value store, you're trading off space for time because you have to do the compression and the decompression. But I think in the metrics that you use to evaluate this, Did you consider at all the energy implications of?
Oh, you mean the CPU utilization rate?
Well, yes, I suppose kind of the extra CPU you're burning as opposed to the kind of memory you're maintaining. And also, did you consider kind of utility computing costs? Like if you did this on AWS, would it be cheaper to hire more RAM or to hire more CPU cycles, I wonder?
Actually, in our paper, we have a CPU cycle diagram for our work and RocksDB and Zip and all other data stores. Actually, to be honest, our work and RocksDB with compression, they have a higher CPU consumption because of compression. But due to the strategy we introduced before, our work can have about 20% consumption reduction compared with RocksDB when both of us enable LZ4 compression method. And if you are very interested in that part, you can check our papers for the diagram. And we have some explanation at that. Thank you.
All right, let's thank the speaker once again.